let me make a little bit of a story where the problem is starting. So the story starts almost 1 century ago with a novel. So this is a novelist, it's not a scientist, okay? Frigyes Karint is a novelist from Hungary. He wrote the novel Chains, and in this novel, what he imagines is that there is a group of friends sitting at a table and discussing how people are tied by means of their social relationships. And one of the participants, actually, of the table proposed that any person out of the entire population of the Earth, at that time it was about 1.8 billion people, and now it's 8 billion people. This would open another big question, but we will leave for the next talk. Could be reached using nothing but each personal network of acquaintance. That is, you can have a link with another person, this other person with another person, and to form a chain. Person is betting that the resulting chain could be of no more than 5 individuals. So this coined the expression 6 degrees of separation, which means that you are 6 steps away from any other evidence of the globe. So if you want to contact Mr. Trump, if you want to contact the Pope, if you want to, you have the network of acquaintances, maximum 6 steps. And this has nothing to do with science, it's just a novel. This is just something, so one can say this is just, you know, in the 60s, the first experiment on social distancing was proposed by Stanley Milgram. What Milgram did is took a bunch of 1,000 farmers in Nebraska, this state in the United States. They were farmers, and he gave to each one of them to reach a broker in Boston. So there was no way that the farmer could not directly the broker. And what Milgram suggested is to write a letter to one of the person that each farmer was knowing, and the person to be chosen is the one that the farmer is supposed to be the closer one to the broker. And then, of course, the receiving partner should write another letter just to form a chain. And this was the distance in terms of number of letters that were needed from the to the target, and he found 6. So very strangely, he found 6. This experiment was actually repeated on 2003, exactly the same experiment, but now with male, and therefore with a much larger number of people, not 1,000, but tens of thousands. So the Columbia University could collect 24,000 chains at a planetary scale, not only Nebraska, Boston, but from any other place in the world to any other place in the world. Once again, the average number of steps was 6. So what is the magic behind 6? What is the magic behind 6? Moreover, later on, you have now very large social systems. So people started to study, the properties. The most important property in this case is the diameter, which is the maximal distance between 2 elements of the network of very large social network. For example, 2007, these 2 fellows analyzed the data of 30 billion conversations among 240 million Microsoft Messenger, path length 6. Wow, another time 6. Then in 2011, it was studied the average degree of separation between 2 randomly selected users of Twitter, now X, and this was less than 6. 3.435. And finally, in 2011, the third nation in the world, because the first nation is China, second is India, and the third is Facebook, because you have 21 million users, okay. Friendly link. What was analyzed, and it was found that the average distance is less than 6. So now there is the problem. What is the problem? The problem is that in between the 1,000 farmers of Milgram and the 21 million users of Facebook, orders of magnitudes. I group this network on a structure like a ring, a lattice, and so on. It is easy to show that the maximal distance between two nodes scales linearly with the number of nodes. If this would be the case, I should see a tremendous difference between the 1,000 farmers and Facebook, and I don't see it. But then you can argue, well, we know that now we are living in a small world network, that is, we have this Strogat's small world structure, and so on and so forth, scale-free, blah, blah, blah. Very good. It is very well known that in scale-free networks and in a small world network, the diameter scales logarithmically with the size, which is less than linearly, but logarithmic of any order of magnitude, you should see. And you measure against. Is it possible to grow a network in an ultra small world way, in which increasing the size leads to a renormalization of distances such that the diameter is independent on the sides? Okay? So the main question is, how can I build a model which gives me a network such that the diameter, the maximal distance between these two, is independent on the number of nodes? And I will show now that when you do this and you answer this question, this number. The beauty of this is that we were looking for a way, of making the diameter independent on the sides, and the only way to do this. In order to do this, our starting point was the following. What is the characteristic that makes a social network different from any other, especially from technological network and biological networks? The clear characteristic is that social networks are made of rational agents, by persons, by us. So these rational agents are making choices. Choices following some, rational, route. And therefore, let us adopt a game theoretical approach as a model for evolving the network. That is, the network is following some rules. And the rules are very simple. We imagine that a person like me, when asked to decide whether to make or not a connection, it looks for a compensation between the cost that I have to pay for making this connection and the benefit that can I have in that connection. It is convenient for me to make a connection. Rule, for example, in proteins are not calculating the following. The network is an agent, this red woman. Of the game is suppose that this red woman stays with some friends, does a set of actual friends, and asks herself, is it convenient for me to stay with these friends or to change? The actual friends, the friends that I have at time t, and I have a group of potential new friends, which is my changes. You see, the potential new friend contains more people, this other woman that is not here, may eliminate some others, so you can change your neighborhood. And in order to decide if it is convenient or not, this lady asked herself, how much would it cost me connecting with a new friend? How much benefit would I get? And then very simply, if the benefit is smaller than the cost, it means that the move is not good, so I stay with the actual friends. And if the benefit is larger than the cost, I move. Okay? So this is the game that actually evolves the network. And therefore, as you see here, the decision is based on a balance between payoff and cost function associated with the change of neighborhood. So basically what I have to do is to define a payoff and a cost function. And then I have this game. Cost. The cost is very simple. I repeat, I don't want to make a model of a real social network. I want to make a model zero for which you have this property of independence from the size. So the proposal is very simple. Assume that if node V pay a unitary cost C larger than zero to maintain a connection with another node U. And that node U cannot refuse the connection paid by V. This is, for example, not the case of Facebook because I have to ask the friendship and the other one has to accept the friendship. In this case, I do something even simpler. I take the entire cost and you cannot refuse my connection, which for you comes for free. So this is very simple. If I have a connection, I have to pay 7 times C. Very simple. And for the benefit function, we are rational agents, we want to be influencer. All of us wants to be Chiara Ferragni, so everybody wants to be influencer, so we want to be in between, to increase our visibility in the net. Especially because Chiara Ferragni, not now, but in the past made some money, much more than a physicist can do normally in his life. So, to the idea of visibility, the function of any pair of nodes that is in the network. Between the center and V, all from to T, from with number of shortest path. Possible. And this needs a little bit of refinement because it's very different if I am a unique intermediary between S and T, or if I am one of the many intermediaries between S and T. I will refer to the weighted between the centrality, that is, I weight this fraction by a function which is, strictly decreasing function of the argument, and the argument is the length of the shortest function. If the length is short, I'm very important. The length is long, I'm one of the many, so I have less importance. You do the shortest for each shortest path through you with a function which is a strictly decreasing function of the length of the shortest path between us. Okay? Very simple. So and I have the benefit, and I can run the when the network reaches the Nash equilibrium. What means the Nash equilibrium here? It means that the network evolves and it reaches a configuration which is frozen because I cannot make any move in this configuration because all possible moves in this configuration are prohibited in that they will have more costs than benefits. So, so to say, configuration of this game to you. Sorry. No. Yes, with the rules you play. Show you that conversion equilibrium. Play one node with a very large degree, so at least one hub. And we know that actually social networks have much more than one hub. But at least you need one. More important, so 6 theorems in this paper, we demonstrate that this node at a maximal distance 3 from this node, which is the 6 degrees of separation, because if I do any node of the network, to this node, maximum to get to the other node. So we have is 6. Insist here on the mathematical proof of the theorems, which are very and in physical review X, so you have to explain the concepts and idea why you have this. Sets. The one going back to Euler, I give you important information. Network theory didn't start in 1999 as people normally claim. It started by Euler 3 centuries before. Huge theory. Independent sector, click nodes, connection among them. So if I take 2 of these nodes, there isn't a connection of the graph. So if you look, for example, the figure here, you see that the nodes A, B, C, D plus the blue nodes are one independent set. Because you take 2, say B and this, there is one intermediary, there is not a direct connection. Which is still larger than 1. What is this? Sorry. Sto facendo un tour che non posso pubblicare. I should have done. Okay. The nodes, the distance between a pair of them is larger than L. Go to the figure. Folded independence because you and you have 2 intermediaries. There is no connection. No. Yeah, you need the two independent sets in the classical one independent set, if nodes belonging to SL do not necessarily belong to SL plus 1. The vice versa is true. So if you belong to SL plus 1, you certainly belong to SL, but not vice versa. Okay, so this is clear, no, from the picture. Look at this situation. From two nodes, 1 and 2, which belong to the one independent set. Between 1 and 2, 2, 3, 4, 5, 6, that are making the shortest path. Between 1 and 2, for two connections, 1 to 1. This is a legitimate move of the game, and this move should be repeated in the Nash equilibrium, because otherwise it's not a Nash equilibrium. That node 7 is by bridging 1 and 2. Multiplicity of the shortest path. The 1, 2, 3, 4 intermediaries, now there is 5. So, in terms of between the central other that just already were existing. So in this means that I have a little game, and therefore I can have a sizable one independent set in the Nash equilibrium. I can have one independent set of given size without having any problem situation. Independent set. They have no direct connection, single intermediaries. 3A, 4B, 5C, 6D. This is the definition of two independent sets. Now, node 7 is bridging. How much is the gain of node 7? And the answer is set. Depending if it is a male or female, connected shortest path. So here, he merged to 7. Because the shortest path is now through 7, and it's unique. Tremendous gain in doing this. And two independent sets are not compatible with the Nash equilibrium. So in the Nash equilibrium of the game, you cannot have two independent sets because we have an external node bridging the two independent sets and have sufficient gain to allow this move. So the independent set cannot exist in the Nash equilibrium. On this node 7. From 7. And node shortest path would be in the two independent set with 1 and 2. And we just demonstrate that in this case, node B will bridge node the question mark. So this is impossible because in this case there would be a direct connection from V to the question mark, exactly as there is the bridge here and there. There will be the bridge with a member of the two independent set. Okay. So you have this stuff extreme from any other node, because you cannot have nodes of distance 4. Or that you have the 6 degrees of separation. Prove this because, you know, this then prove this. Prove this, and I skip many details because I don't want to enter into this situation. So the following: I take an initial network, initial condition, and from this initial condition, I evolve the network towards the Nash equilibrium. Is of the network. So we start from networks of few nodes to 1,000 nodes. Okay. Network which happen because so I have certainly help of this an ensemble of 1,000 of that size. Line. I already have a fantastic, beautiful scaling with the size. This is very maybe I don't know all the condition. This we got to see here the blue line. This is a log log. Okay. To the Nash equilibrium. More of 10,000 equilibria, each one originated from the different initial condition. Calculate again D, and this is the green line. You see? You increase, then you go to 6, and you are independent on the diameter. So, from on, which is 100 nodes, more or less, so 2,000 nodes, you get the equilibrium state, and small world state in which the diameter is not dependent on the size and is equal to 6. You of the network, because you make and connections. In this case, we only have obviously changing the distances. Game. You know how this you have added to the final stage. Condition and the same number of connections. With benefits and costs. Okay, and make this number of, so you obtain the same density ensemble, which they plus a number of units which are being randomly exactly in the same quantity needed to obtain the Nash equilibria. This is below the blue line because you increase the density, but what is more important, the scaling does not change. So a small work is to run the scaling equilibrium state. This many considerations. I want to what you are doing. You are fixing the diameter, but you don't change the other property of the network, because the connection that you have to put is not So this original network, the correlation property, realize the distances. You can have all the other properties that you observe in certain networks, such as a certain point. Zero is just a very simple compensation rule. So the compensation benefits is the natural interaction strategy of rational agents, because we are rational. If not rational, principle mice logical of so you can make or sea transportation network. There you have the same problem because airports and ports, which are the nodes, no, they may increase the volume of trains or tourists in being in between, so in having the maximal betweenness, in being in between the main routes of interchanges of passengers or goods. So you design a network, and this network to be in this ultra small world state. Huh? Fruits of the stupidity in replicating the DNA. So, and so agents you between a certain this long evolutionary path. The possibility mechanism could be of their evolution. And instead of being between us, random perturbation, which is the selection, the Darwinian selection mechanism, global efficiency, that is, and the system selects the most fit in terms of the maximal resilience or the maximal local and global efficiency. Efforts are indeed to make model Z function like on final equilibrium state, which reproduce the characteristic that you have in networks. To a journal in physics, okay, which is Physics Reports. I think everybody knows Physics Reports. It's 29.5. These are very good numbers for 49 for now. Wow. For the of nonlinear dynamics and complex systems, for review monographies to be published by this report, because only, and so I have to make the invitation for you. Which is very important because you have to this have a review in this subject, why it's important to have it, and so forth. Then coordinate the corresponding author with the observation. Up to the editorial board for possible invitation. So to paper to physics report. So I finished.
Very much time. Fascinating talk, Stefano. Comments, questions?
Yes, I have a question. You are in a network, okay, and many times you only know your neighborhood. While in this very interesting study, apparently any node can decide suddenly, due to the payoff and benefit balance, to connect with any other node. So I wonder how, and also not only in social, but also in biological networks, how can I assume that the node will penetrate simultaneously of everything? Thank you.
Exactly the answer to your question.
Okay, great.
You have to know the betweenness centrality. And so between two possible, so you have to have knowledge of your network to decide whether or not a sixth theorem, that's why seventh theorem, for the definition of the 6 degrees of separation. 7 is this, and we said 7 is the number of everything, so we cannot exceed the 7. And if you imagine to know only a neighborhood, a knowledge of only one neighborhood, which is specified to number h. And when it goes to infinity, you recover the other one. The original connection. H is some integer number, strictly larger than 2, and you have this formula which holds. And actually, this formula holds always for a sufficiently large node. The given state of the network, the node V is linked to all of the nodes by more than H links. What does it mean? It means that you will always have a constant diameter. Always be a number, because we just the situations work, but you have to, instead of 6, you may have 8 or 2 or whatever. Okay. So it's the same. You project a given dependent set, not necessarily the dependent set. If you project the dependent set, you will have 4. If you 5, no? The main idea. No. Not in this work.
Ci sono qualcuno da casa il microfono.
Please.
Yes, so thank you very much. It's very interesting. And humans, we try to maximize this popularity, right? But perhaps the nature is minimizing also the cost of being destroyed by a virus. And I'm thinking like a virus can be someone that knows, that can have all this information really easy, because it's so connected that
yes,
you don't need to know 20 in the small world. You just can get to you, for example, because you are very popular. With few interactions, if you need to eliminate you, for example, right? violent or whatever. So perhaps, I mean, this is a follow-up of your last point.
But we were interested in biological network because we wanted to see if there is a way, maybe this is a crazy idea, of modeling evolution, Darwinian evolution, okay? But what you say is also another evolutionary principle. The idea is that instead of having probabilistic rules in growing a network, like the Barabasi-Albert, no? or any variation, in which you a priori give a probability to connect, to make the growth of a network following a game, following some compensation rule. Then what is cost and what is benefit certainly will depend on the problem that you have at hand. So in a case of social networks, it's reasonable to imagine that everybody wants to be an influencer, so between the centrality. But in other situations, the benefit function could be, as you said, different. So the idea is launching a new way, so to say, of growing network in a way that they have controlled distance and not scaling distances.
So I'm a biologist. Okay?
Yes.
So you are assuming that all the nodes are identical. They do not have a weight on
Yes, yes. I assume that's, of course, I told you this is a model 0. After we published the paper, there are many, many people who contacted us. They wanted to have a real model or real social network. But in the model 0, everybody is identical. Then you can imagine instead that each node has a different or slightly different value, some coefficient in front of the fitness coefficient in front of the benefit function. But this, of course, complicates much more the issue. And
I have a question, Josephine. In your theorem, how is important the assumption that the cost is constant? It's not dynamic.
this is another important stuff. No, sorry, I had to go back. In the theory, you can, these are valid for constant cost, of course, but also for cost, you see, which depends on the network size up to a given scaling. So normally you can say, okay.
For any function?
No, up to a given scaling. I think it's cubic or quartic. So if the cost increases too much or decreases too much, then you have to start having problems. So one is that the cost is a constant, and the other one is it scales itself with n, but less than a given power. And this is important because you can have situations in which increasing the size, for example, in biological system, if you increase the size and you have a geometrical embedding, no? Increasing the size means increasing the real distance. If I want to launch a link from here to there, I have a larger cost with respect to a link from here to there.
So the theorem in which there is the bound of C by the formula is a change on the formula?
No. There is a comparison of scaling, and the comparison of scale is valid up to Cn smaller. I don't remember if 3 or 4. You can go and see. For C constant is obvious. It's n to the 0. C of n is n of the 0 to the 0. But you can have n to the first, the second, to the third, and it's still valid. When you start increasing too much this, then you break up the theorem.
And there is the number in your theorem.
Sorry?
Is in the slide that you show on the theorem concerning
the other theorem, this other theorem was different. It was a little bit different because it was this one. Yeah, it was for local knowledge.
Okay. This last part,
Sì.
H, that is fact, remain valid when you use C, not constant, but
This I don't know. You have to look at the theory. This I frankly don't know. I don't want to say something that.
okay.
But it's a good question, of course. C can be. Now, in social networks, C does not depend on the sites.
Yeah.
Because when you make
Yeah.
a friendship.
But in biological network.
But in biological network, you don't have the between the centrality. You know. So. Yes.
Thank you for the talk.
Eh?
Thank you for the talk. Is it always that this game reaches a natural equilibrium, especially when you have removals?
The answer is that there can be pathological conditions indeed. When you only add with it, so you always reach the equilibrium. By the way, the equilibrium you reach, strictly speaking, is not a Nash equilibrium because you may have something better in removing. You never know. When you add and remove, you may have some pathological initial condition that does not reach to the. So in this case, it's when you obtain the Nash equilibrium, which is in any case the very, very large majority of cases, you have this problem.
Thank you. Okay, time to move on to the next.
Yes, please.
Again, many thanks, Stefano.